So previously, we've seen that the derivative of e to the x with respect to x is equal to e to the x. That is, the derivative of the natural exponential is itself. What about other exponential functions? What if we want to find the derivative of 2 to the x dx? Is that equal to 2 to the x as well? Well, if you go back to the proof of this statement, the squeeze theorem argument we used to derive that the derivative of e to the x is itself was dependent upon e to the x. That is, we derived some inequalities for which those inequalities came from it being e. So we shouldn't expect that other exponentials will be their own derivatives. There's something special about the number e. But what can we do? It turns out that if we use the chain rule, we can actually combine what we know about the derivative of e to the x and apply that to the derivative of any exponential function. So if we want to, so what we're going to prove right now is the derivative of a to the x with respect to x, where a is any exponential base, it's just a positive number. We get that that's going to equal a to the x times the natural log of a right here. So before we proceed to do the proof, I want you to kind of examine this for a second. Okay, the derivative of a to the x is a to the x times the natural log of a. If we think about that in terms of e to the x, after all, e is a number that's positive, so it applies here. If we take the derivative there, if you use this formula, this would tell us the derivative is e to the x times the natural log of e, which the natural log of e, since natural log is base e, this is just equal to 1. You get e to the x times 1. So we can reproduce that e to the x is a special case of this. And so the way I like to think of it is this right here is some type of tariff that has to be paid. So that in terms of calculus, the currency should be base E. But if we are using a different currency like base 2, base 7, whatever, we can still take the derivative, but there's sort of a transaction fee, a tariff that we have to pay in order to calculate the derivative of an arbitrary exponential function. So how are we going to prove this with the chain rule? Because chain rule is about function composition, f composed with g of x. What's the composition in play right here? So it takes a little bit of effort, but notice it right here. If I take a to the x, this is the same thing as e to the natural log of a to the x. I want you to think about that for a second. If I take a to the x and I add to it 2 and I subtract from it 2, most will have no arguments there that, oh, the plus 2 minus 2 cancel out, so it's just a to the x. On the other hand, what if I take like a to the x and I times it by 2 and I divide it by 2? Again, not a lot of conflict there. If you divide things, if you times and multiply by the same number, it just cancels out. Well, what we're seeing right here is that same basic idea. Here, we're going to exponentiate by e, and then we're going to logarize. Is that even a word? We're going to logarithm. I'm using it as a verb right now. We're going to logarithm by e, for which these are inverse operations. Exponentiate by e and logarithm by e are inverse operations. So the composition of these two does nothing. So that's why equality follows right here. But then the benefit of introducing the logarithm is that by logarithmic laws, we can bring this fact or this exponent of x out in front as a factor. And so now to calculate the derivative of a to the x, it equates to taking the derivative of e to the x times the natural log of x, which we'll see is to our advantage to do so. So why is that? Well, the derivative of a to the x with respect to x, like I said a moment ago, it's the same as taking the derivative of e to the x plus the natural log of a. Now, I want you to focus on that exponent for a moment. Look at that x times the natural log of a. Writing this in slightly larger font on the screen right here, we have composition of functions now. The exponent of the exponential is this inner function, x times the natural log of a. And then the outer function is going to be this exponential function, for which, by the chain rule, we're going to take the outer derivative right here, e to the x times the natural log of a power, and then we have to take the inner derivative right here, which we're taking the derivative of x times the natural log of a. Now here, remember, we're taking the derivative with respect to x. X is the variable that's changing. The base a is fixed in this consideration. And so if you take the derivative like a 2x, we know what that is. That's just going to be a 2. If you take the derivative of 5x, that's just going to be a 5. The same thing also applies here. The natural log of a is just a number, like 2 or 5. Sure, it's probably an irrational number, but it's still a number. It's just the coefficient of x. So when you take the derivative of the natural log of a times x, the derivative turns out to be the natural log of a. In which case then, when you look at the outer derivative, wait a second, the outer derivative is just this guy right here, which this one, remember, was a to the x. And so you make that substitution and we get a to the x times the natural log of a. And so this then allows us that if we want to take the derivative of, say, like 2 to the x with respect to x, this will just be 2 to the x times the natural log of 2. It's just like e to the x, you get back itself, but then you also have to pay the tariff because you weren't working base e. How about this one? If we take the derivative of s, which is e to the t. Well, the derivative of s with respect to t, you're taking the derivative e to the t right here, where you're going to just get e to the t times the natural log of 3. Again, remember to pay the tariff. That's the most common thing that students mess up if they take a derivative of an exponential other than base e. They sometimes forget to pay the tariff. All right, what about this one? This time s equals 8 times 10 to the 1 over t power. So if you want to calculate the derivative of s with respect to t, we have to take the derivative of 8 times 10 to the 1 over t power. Well, since 8 is just a constant multiple, we can bring it out. And so we're going to get 8 times 10 to the 1 over t power. And much like we saw in the proof of this thing, there's a chain rule going on here. There's going to be the inner function of 1 over t, and then there's the outer function, which is 10 to the power of something, exponentiation base 10. And so when we calculate the derivative here, we're going to get our outer derivative, which will be 10 to the 1 over t times the natural log of 10. You have to pay the tariff with the outer derivative. And then the inner derivative, well, we have to take the derivative of 1 over t, which you might want to think of 1 over t as t to the negative 1 power. That can be very useful here. So then the power rule applies. So we're going to get 8 times 10 to the 1 over t times the natural log of 10. Next, when we take the derivative of t to the negative 1, we're going to get negative t to the negative 2. And so putting this all together in a slightly more condensed, simplified format, we're going to get negative 8 times the natural log of 10, because those are just the numbers I'm going to put in front. They're the coefficients. We're going to times that by 10 to the 1 over t power, and this sits above t squared right there, thus giving us the derivative of this function. So we can combine these exponential functions with the other functions and derivative rules we've developed so far. We can take the derivative of any exponential base. Just make sure that you pay the tariff when you are not working base e.